Hi everyone, how's it going? We'll start in about 5 minutes or so. Alright, we've hit our 4 AM GMT starting time, so let's kick off a little bit. Today we're running things in the opposite order, so we're going to start with a technical tutorial on global variables with Fologram in Grasshopper, and then Sean will jump in and show you a couple of new definitions that use globals within them, so you can apply some of the technical knowledge from this first session. So global variables are components which are specific to Fologram, and they oh, hang on a second, I'll just respond to a question. Alright, I'll let Sean follow up with you, Alexis. Yeah, global variables are a unique component to Fologram. They work quite differently to how many other Grasshopper components work, a lot like the state gate does. And what they allow you to do is store data within components and then access it anywhere in your definition without necessarily having to create a wire, like a direct parametric link between the global variables. So I'll give you a few examples of how this works and what I mean. If you've done any scripting before, if you've written any code before, global variables work a lot like a dictionary in programming. So they essentially have a name, or in the case of a dictionary, they have a key, and then that key refers to some value for the global variable. So when we're using globals in Fologram, in Grasshopper, we need to work in a similar way. So when we create a global variable, we give that global variable a name, and we assign some value to that global variable, and then we can use the same name elsewhere in our definition to retrieve that value and use it to do stuff. So to create global variables in Fologram, we use the set global value component. Okay, so what that does, if we drop one of these down, is it makes one of these components. You can see it doesn't actually output anything because it's being stored by Fologram internally in the Grasshopper document. It only has one input, and that's going to be the value of our global variable. That global variable can be anything, any kind of object. So it could be geometry in Rhino, it could be a material, it could be a list of numbers, it could be text, it could be a color, it could be anything. We can plug anything in there. And then it has a name here. So globals by default are called global. But if you right click on the component, you can change the name of your global variable here. And this is doing more than just renaming the component. So you can typically rename components in Grasshopper. For instance, if I make a script component, I can rename it and call it whatever I like, but all I'm doing there is changing the name. Whereas with a global variable component, this name works slightly differently. So when you change the name of the global here, you're actually changing the way that component is working internally, right? So I'm going to call this my demo or something like that. So now I've created a global variable called my demo, or I've made another one down here called my number. So let's use this as an example. And here I'm just plugging in some data into my number and changing the value. So as I change that value, the value of a global variable called my number is going to be updated. If I want to update the value of my global variable, I can update it from anywhere in my definition. So this is pretty cool. So here I've got another set global variable component. In fact, let's just make this from scratch. Alright, so here I'm creating one called my number, and I'm giving it a value. If I wanted to change the value of my number from somewhere else in my definition, I can drop down the set global component. I can change it to the name of the variable that I want to set, or the global variable I want to set. I have to make sure it's exactly the same. And then I can plug in whatever I want, and it'll update the value of that global variable. So now, if I set this to a point, this is a little bit counterintuitive, but my number will be a global variable which is storing a point. Or if I plugged in a number slider, now I've changed the value of my global variable called myNumber to being a number again. So you can set this value for a global variable from anywhere using the set global variable component. Okay, so that's creating and updating globals. Now, how do we use them in our definitions? So the other component in Fologram that works with global variables is called getGlobalValue. And what that does is it retrieves a global value from your document, your Grasshopper definition, that matches a given name. So when you make one of these, again, its default name is global. Again, you can rename this to whatever you want, and it'll retrieve anything that matches that name. So here, I've used the getGlobalVariable component called myNumber so that it matches this one that I've set over here. And this will get the value of my number when I create it. Now, a few things that are really important to explain here in terms of how the behavior of this component actually works. So I'm updating the value of my number over here using my set global component, but you'll notice it's not updating over here with my get global component. And that's because by default, the way the get global component works is it only retrieves new values for a global variable when certain conditions are met. So the first condition is if we explicitly ask the component to retrieve it by clicking on this little refresh button here. So if I click on that button, it'll get the current value. I just happen to have that on 10. There we go. So if I change it anywhere in my definition, all of the get components, they'll detect that a change has been made, and so this little refresh button will appear, but they won't actually update. They won't output the new value until you ask them to by clicking on that button. So that's the first way that you can update them. The other way that you can update them, and I'll use that as a little demo down here actually, is let's add 1 to this value. The other way that you can update a global variable, the other way that you can retrieve an updated value for a global variable is by changing the component or updating the component that the get global variable component is connected to. So if I have a get global variable component connected to something in my definition, so here I'm using it as the input to this addition component, and I change the value of this addition component, that will pull down the latest value of my number. So let's try changing this here. You see it's pulling down the latest value. Now this is extremely different to how Grasshopper components normally work, because updating a component downstream from a component in Grasshopper does not normally update components upstream, so to the left of the component. Changing something here doesn't normally trigger a change in components which are before it, that precede them. But with global variables, because any component in your definition might be changing this one, not just components that are explicitly input to it, because the get global variable component doesn't actually have any inputs, it's retrieving things wirelessly, let's say, from the document. We've slightly changed the behavior of these components for when and how they update. Okay, so just keep this in mind. So if the value of this global changes somewhere else in our definition, so see I'm changing it over here, I've set it to 5, let's say, and we can check that it's equal to 5 using this little component, forcing it to refresh. It's 5, great. Now 5 plus 1 is not 11, right? Now there's two ways I could update this. One would be by clicking the refresh button on the component, as I demonstrated before, and the other is by making this downstream component update. So I can update it by changing this other input here. And now we have 5 plus 0, and we're getting the right result because we're using our most recent output variable. Now, as you start using Fologram more, you'll understand why this behavior is useful. And in a second, I'm going to show you how it's useful with some practical examples. But to give you a very sort of high level and rough idea of why we have this particular behavior, it's because very, very often you want to be able to retrieve the value of the global only when the rest of your definition is updating. So let's say maybe you press on a button, that press updates a whole lot of components, there might be some global variables used as inputs, and we're getting the current value of the global just when we need it, so when that press is executed. And that's why this behavior works in this particular way. Okay, the last way to retrieve values from global variables is dynamically. So to listen for changes to the global variable and then update the value automatically whenever they change. So rather than prompting us to update with the little refresh button, or rather than waiting for a downstream component to pull down the latest value of a global variable, we can just automatically update our component. So I'm going to copy this down here so you can see what I mean. So here's my component which is setting the global variable. I'm changing it, ding, 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 ding. And this component here is dynamically updating. As soon as we detect a change to that value, this component's updating and telling us what the value is. Now we have to set this behavior explicitly on the component if we want the getGlobalVariable component to work in this way. And the way you do that is to right click on the little empty space at the start of the component and turn on dynamic updating. You have to be quite careful with dynamic updating, because if you are doing something like this, let's say, we're getting our value of a global, we're adding one to it, and let's say I want it to be clever and then reset the value of my number to be equal to my number plus 1, like that. That's going to make an infinite loop, because I'm going to update my number, this component then goes, oh, I've updated, it'll rerun these components, re-update my number, and then that code, that little bit of grasshopper definition, is just going to run forever. Now, Fologram is clever enough to detect infinite loops, most of the time at least. And so here we're working out and we're getting a little error saying that we have a recursive loop detected. Please don't dynamically update this component. But that won't always be the case. If you have very complex definitions, we can't always detect recursive loops. And so it's just worth taking care. If you have a definition which is dynamically pulling down and then changing the value of some global variable, it's easy to crash Grasshopper if you create recursive loops. Okay, so now we've got getting and setting covered. Let's look at why these global variables are useful, and let's look at some cool stuff that we can do with them. So you can use global variables to create loops and recursive models in Grasshopper really, really easily. Some of you might have used things like Anemone before, or HoopSnake. They're two plugins that let you build loops in Grasshopper and run parts of your definition over and over and over again. Plugins like Kangaroo internally are iterative. They're simulating your model over and over and over again. Or if you've written scripts, maybe you've written loops as well. Now we can do this with Grasshopper by essentially carefully creating the behavior that I just talked about before, where we are taking a global variable, changing it in some way, and then rerunning that definition again and again and again. But we just can't do that with dynamic updates. We have to do it manually, let's say. So here's a little demo. So I have a curve here. I'm just going to reset this component so I can't see it. So I've drawn a curve. It's this one here. And I've created a global variable called current curve, which is initially just set to this shape that I've drawn. And then I've made a really simple Grasshopper definition, which is getting the current curve, dividing it up into some frames. And I'm going to make sure I'm using the current curve here. So we're just dividing it up into some frames, deconstructing those frames, moving the points from the frames, and drawing a new curve. So basically what this little definition does is it's offsetting the curve, but it's offsetting it in 3D. So the typical offset command just offsets in the curve plane. or in XY, whereas this is offsetting the curve in 3D. So once we've done that, we've made our new curve. I'm then changing this global variable. So I'm saying, okay, well, rather than using what it was before, let's use what it is now, which is this new offset shape. And you can see that this global variable component. It's detected, oh, okay, there's a new curve here that's been made. Do you want to update it and use the most recent value? So if I click on this, now this little bit of grasshopper definition has run again, and we've created another new curve, and again, and again, and again, and again, and so we have this iterative tool for offsetting all of our curves. Now I need to figure out why we've got this thing happening. In fact, let's just try saving these in a global variable. So I'm going to reset it. So we can see what's happening over time. What I'm going to do is let's make a global variable called curves. And I'm just going to essentially add our current curve to a list of all curves as we tick along and do this. So tick, 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 tick. And you can see every time I update my global variable, we're offsetting it to make a new curve, saving that into a list, and we now have a sort of an iterative offset tool without writing any code at all. Now, to make this run over time like a simulation, you can just attach a timer to the get global variable component to force it to update with some frequency. So now it's updating 10 times a second, and we have a cool little curve offsetting tool, which is kind of nice. So this will keep offsetting and make these sort of interesting waving patterns just because of the way that this divide and offset algorithm is working. So making recursive loops, super duper easy using these global variables. You just have to be a little bit careful. This means that you can use Fologram's global components to build all sorts of different simple simulations. So you might have seen a sort of diffusion limited aggregation examples online somewhere that people have done with code. You could make those with global variables pretty easily. Or L systems, so branching geometries, those could also be made with global variables pretty easily. Now in terms of Fologram, how we're typically using global variables is essentially to store bits of data in your model that are going to get reused over and over and over again, and prevent us having to remake the same functionality in our grasshopper definition multiple times. A really common thing that you might end up doing with global variables is building applications where you have custom control over how the cursor works on your mobile phone. So the default cursor on a mobile phone is when you tap on the screen or drag on the screen, we're projecting a line out from where you're tapping until it intersects with the nearest detected surface in physical space. You can slightly change that cursor behavior in the Fologram settings, so you can have the cursor be always on and just projecting out from the middle of your phone, and you can also have it be always on, projecting out from the middle of your phone, and a specific set length from your phone, depending on what you want to use that cursor for. But Fologram doesn't by default give you any control over, say, whether or not that cursor snaps to geometry. So that's something that you have to build yourself. Like maybe you want to make a modeling tool where you can snap onto surfaces and draw curves on them. Well, how do you build that functionality? The way that you do it is by using something like this. So I've created a global variable called cursor, and that's going to be used to store the position of my cursor. And then if you recall from yesterday, I've got a state gate here with a value list that's letting me choose on my phone whether or not I'm snapping to curves, sorry, not snapping at all, snapping just to curves, or snapping to all geometry. So I've got that in my Fologram UI on my mobile phone. When I have no snap at all turned on, I'm just using the endpoint of my cursor. So that's whatever the Fologram default is. when I have snap to curves turned on, I'm using the geometry pipeline component in Grasshopper to get all of the curves in my Rhino model, and then I'm using the pull point component to pull my pointer position onto the nearest one of those curves, and then using that to set my global variable instead. So this is essentially what you need to build a snap to curves tool. If I have snap to geometry turned on, exactly the same, pull point, updating my cursor, but this time my geometry pipeline's using all kinds of geometry, not just curves. So this is really nice because it kind of means that we've abstracted out from our Grasshopper definition 3 different behaviors for our cursor, and it's very clearly defined where that happens in our Grasshopper definition. It's happening here. And then elsewhere in our definition, we also have nice, clearly defined ways to reuse that cursor position over and over again as we need it. So for instance, we might have a couple of components here which are drawing our cursor. So I'm dynamically pulling down the cursor position, which I can do because I'm not using this cursor position to update the cursor position at all. I'm just using it to draw something. So I'm getting it, drawing a sphere, sending that back to my mobile. And then down here, I'm using the cursor position so that whenever here I'm tracking all of my devices, detecting what state they're in. I have a state gate which updates whenever I press on my screen. If you remember from yesterday, this is the same pattern that we went through before. And whenever I press, I have a global variable which is storing a list of points. I add my cursor position to it, and that's really all I'm doing. So basically, whenever I tap, I'm saving the current position of my cursor into this list of all points. And then over here in my another part of my definition, I'm using that all points variable to draw some more spheres. So we've managed to compartmentalize our Grasshopper definition into several distinct parts that are all using the same data, the same cursor position, but without necessarily needing to have this complex spaghetti that connects everything together. And that helps keep our Grasshopper definition really, really clean, easy to understand, easy to extend, and also fast and performant because we're not passing data around and updating components when we don't need to. To give you a quick sense of what this would look like if we didn't have global variables, well, you can start to think about it really. It's that has to go there, this has to go there, this has to go there, this has to go here, this has to go here, this has to go here, and suddenly you have spaghetti. It's really not nice at all. In some cases, you can't even build Grasshopper definitions without being able to, or build particular apps without being able to explicitly break this data flow in the way that globals allow you to. Okay, one more example of using globals. This one's a nice simple one. So let's say, for instance, you want to build a drawing app, and Sean's going to go through this in quite a bit more depth in about 5 minutes or so. So what globals allow you to do is, again, this is another example of breaking up the functionality of your Grasshopper component into different disconnected parts. So building a drawing tool in Folograms, it's quite simple, and you might use that drawing tool for different purposes of assisting with fabrication. So for instance, let's say you have we have clients that are using Fologram with section rolled steel fabrication. They might section roll a component, and then they want to be able to bring the shape of that section rolled component back into Rhino, so they know exactly what shape it is in their digital model. They would build a tool which just lets them redraw that shape by drawing curves in space, rather than necessarily having to 3D scan it or anything complex like that. So digitizing physical parts is one application of these sorts of drawing tools. Here again, to build this application where you can draw curves in space, we've created a global variable to store a list of points, and I've initially set that to be an empty, like to have no value. It's just an empty list. Then we've got, we're tracking our connected devices, we're tracking when we have a pointer interaction, so when we tap on the screen. I've set this to only update when we press. So this component updates when we tap on the screen. We can get the endpoint of our pointer and add it to our list of points. So basically every time we tap, we're adding a point to this global variable here. And then in a completely different separate part of our definition, which is in no way connected other than via this global variable, we're listening to changes in our curve points. It needs to be dynamic, come to think of it. Drawing where those points are using some spheres, and also fitting a curve through them and syncing that as well. Now this is red at the moment just because I haven't actually run this app and drawn anything yet, but if you wanted to give it a go, you could. So this makes building kind of, in some cases, conceptually or functionally complex applications really simple, because you can break them up into far simpler components. It makes building Grasshopper definitions a lot more like how you might build the same functionality if you were scripting or programming. You would be defining functions which are as simple and discrete as possible, and then calling those functions to build up more complex applications. So using global variables to pass data around in your Grasshopper definitions allows you to do things like that. No more spaghetti. All right, that gives you a kind of a technical understanding of how these two components work, the set global variable and get global variable components. And now Sean is going to jump on and walk you through a couple of definitions that will show how they are used. Cool.
All right, cool. Hopefully that was an insightful description to how global variables work, guys. So thanks for that, Gwill. So what we're going to do now in this little part of the session is we're going to look at how we can apply that logic to a drawing tool that we're going to then use as a little bit of a design tool later. So maybe the first thing I'll just mention just off the bat, just so everyone can go ahead and get onto it straight away. We're not going to use it like right now, but there's a little example file that I've gone and uploaded. Well, there's two example kind of files, I guess. There's a Grasshopper file, and then there's more of like a template file I just want you guys to download. So if you could jump onto the community forum, I'll post a link to this in the group chat as well, so you can easily access it. If you could just download that Grasshopper file and then those Aruco marker trackers, we're going to talk through a few of these things straight away. So, like I said, we're not going to necessarily start with the rod bending application, but basically I want you to just get a blank Rhino and Grasshopper document up. Use your units as millimeters just for this application, so all of my measurements are going to be in millimeters. So it'd be good if you could just be on the same page. So before we build this drawing application, I just want to quickly talk through a few of the tracking components that are available to us in Fologram, because we're going to use one of these components to use the drawing application, and I think it would be good for us to just start by having a bit of an overview as to what some of those components actually do. So they're pretty fun components and they're simple to use, so there won't be very long technical descriptions, and it should be easy for everyone to get involved and engaged. So what I'm going to do first is I'm just going to start by going over to the Fologram tab in Grasshopper. So I'll just give everyone 1 minute to make sure they've got Grasshopper and Rhino on their screen, and then we'll get it up. I'll also just connect my mobile phone up to my screen as well, so you can all see that. Just 1 second. So there's my phone just on my desk, as you can see there. Cool. And I'm going to go ahead actually and connect it to this empty Rhino session as well. So let's go ahead and just connect a device. So as you'd expect, I'd get a QR code. I'm going to go ahead and scan that guy. And then I'm just going to place it wherever for now. It doesn't really matter too much where we're going to place that. Cool. So you see that I'm connected. I've got my phone sitting here indicating that I'm connected. To use the tracking components, the first component that we want to drop onto the canvas is just under the track area. So obviously we've got a list of big components here, but the first thing that we want to put down is the connected devices component. So basically whenever you're using tracking components in Fologram, the first thing you want to do is grab a connected device component. So let's click on that one and drop it onto the canvas. And I've got a little new funny plugin I've just installed called Bifocals. So what I'm going to do for you guys today is have both the images of components and then the name of the component appearing here. So this little component should enable us to just see both of those things, just in case that's more helpful, so you can easily match them up. So if you ever are lost, just look at that kind of component name and you should be able to double click and type in like connected devices and grab that component. But that just gives you, an indication of both of those things. So straight away to the connected devices, we could have a look at what the actual output this is, because a device isn't really like a curve or something. What we're getting is a list of the devices that are connected to this Fologram session. So right now my mobile phone is connected to this Fologram session, but of course you could have HoloLens connected as well, and you could have an Android phone, I guess, as well connected to the session. That just lists which devices are connected so we can transfer that data into the tracking components. So let's go back to the Fologram plugin tab, and we can go back to the tracking components. And the first one, which is always a bit of fun just to test out straight away, is the track device component. So I'm going to grab the track device component and drop that onto the canvas there. And the track device component takes a device as an input, and it outputs something called a device transform. So we'll discuss what that output is in a second. One thing you'll notice straight away underneath our component is we get a little thing called always. And this is a little indication as to when we are actually tracking something inside of Fologram. So by default, pretty much all the tracking components are set to always. If you right click on the icon, you can set it to a manual tracking. So that would be if we actually, touched or activated our phone or did something. On press is when we actually touch on the screen. If we started dragging, or if we were dragging, or if we were holding onto our device, we're able to go and basically track all of our device transforms based on a state that we're inputting into our device. I'm going to leave it as always for now and just plug that into my canvas. And I'm going to zoom out, and you'll see I get a little mesh of my mobile phone. So as I kind of go ahead and move this around, you'll see that I get a nice preview of my phone moving around in Rhino. So we actually have a little preview of our phone sitting there. Now what's quite powerful about this device transform output is it's something called a dynamic output. And what a dynamic output does is it enables us to draw different types of data out of this output. So right now we can see we can get a mesh out, which is, a indication of our mobile phone, which we could use in Grasshopper if we wanted. We could also get a point out of this as well though. So if I went and place the point location in, you can see I get a little point right at the center of my device transform straight away. So I'm able to track the actual location of my device. And I could also put in a plane and actually get the rotational data of my device. So you see the plane actually corresponds to the device itself as I go ahead and move it around. So straight away we're actually almost able to create like a really simple motion tracking simulation with our devices inside of Grasshopper. So just have a quick go. I might give everyone a minute just to get that relationship set up, and let me know if it's working in the chat or how you're going with that. I just want everyone to be able to track their device. So connect to a live session in Fologram, make sure you've connected, and then just drop a connected devices component onto the canvas and a track device component onto the canvas. Cool. So hopefully that's kind of like interesting and you could see the possibilities. Like my first thought, like one thing you could quickly test out with this is perhaps in the brick stacking application or the design of the wall yesterday, we were creating like a sphere as the attractor point, and you could easily create a interactive brick wall by replacing that sphere with the location of this device, and suddenly you could, you know, move closer to the brick wall and certain bricks will rotate or move around and have this kind of interactive design going on. So another tracking component that I want to talk about just quickly and very briefly, because it's actually not that useful on the mobile devices as much as it is in the HoloLens, but we have a track scan component as well. So I'm just going to drop that into the canvas. Once again, it just takes the device input. So I'm going to plug my device into there. And what the track scan component will output is a mesh geometry of our surroundings. So I think it'll work. So you can kind of see I go into edit mode there, and I can actually see that I'm tracking the surface. So if I went to like the reset, what I'm actually doing here is I'm tracking the location of this hexagonal kind of placement mesh, and I'm sending that data back to Grasshopper. So it's a pretty low res tracking of your actual surroundings there that you're seeing, but it can be kind of useful if you just want to visualize in Rhino what your surroundings is. If you're using a HoloLens device, the tracking cameras on the HoloLens are much more sophisticated, and you're actually able to create these kind of low resolution meshes of the room or the space that you're sitting in and send them directly to Grasshopper with the track scan component. So what I say about that again, just to repeat, is the track scan component really great on the HoloLens, but in a mobile device it just gives you a low resolution scan of those kind of surrounding elements that you've got there. A really important one that we're probably going to use today to do our drawing application is the track state component. So I'm going to drop that onto the canvas, track state. We are going to go ahead and plug the devices straight into there as well. And track state actually outputs a bunch of text text data. So you can see as I hover over there, we've got a little A symbol that indicates that it's going to be a text output. I'm going to go and create a Grasshopper panel and plug that into there. And nothing's coming out of that straight away because you notice how we have always underneath all of these ones. Track state doesn't work as an always thing because what it's doing is it's actually tracking the state of your device. So if I go over to my phone and I hold down onto the screen, you can see that my panel changes to hold. If I let go, it quickly changes to something called release. If we made like a little data recorder, we could actually easily just see what these kind of states are. So I could go and press once and you'll see the indications I get. I get a detection on the screen, then I get an indication that I've pressed the screen, and then I get an indication that I've released from the screen, and then an indication that I've lost that detection initially. I could try and drag on the screen and you'll see that I get a drag output in my tracked state, and I release and lose it again. And I could just hold on the screen and get a hold state on my track state component. So we're going to talk about how this is going to be really useful to us in probably like 15 minutes or so, because we're going to use it in the drawing tool. But the most powerful thing that this can be used in combination with is the state gate, and we'll do a demonstration of that as we move through today's little checklist. So I'm going to go and delete all these guys first, and we're actually going to now start looking at how we're going to build our drawing application using Fologram's tracking tools. So the tracking tool that we're going to use to build this drawing application is one we haven't looked at yet. We're going to look at track pointers. So I'm going to click on track pointers, and I might as well just plug my device into there. And what track pointers will do is it will create a basically a line or a vector whenever you kind of touch your device, of where your application or where your device is pointing. So see this point here on my phone, I'm basically tracking the location of that point through this vector. To give a better indication of what that's actually doing, maybe we could add a device transform. So you can see there's my device, and now I'm just aiming my pointer around on my screen, and I get a nice vector of that phone there going like that. So Ziran, I'm just seeing your message on the chat. We're going to talk about the foam carving study tomorrow. So we'll probably use this as a little bit of an introduction to the tracking, and we're going to apply that in tomorrow's morning's kind of tutorial before we jump on Zoom and discuss how everyone's kind of found the process so far. So you can see how I'm creating this line. So once again, the track pointers gives us another dynamic output. So I could go ahead and track the rays with 3 different data types again. So one data type in this instance would just be a line. So I could dynamically track a line and get, you know, data of a line. So I'm getting that line there. I could change it to a point, and what I'll get is the endpoint of my ray, like that. And then I could also make it a vector. We won't be able to see the vector because vectors don't preview in Grasshopper, but we could do a vector display and just preview that guy with the actually that won't work because I don't have the starting point, but basically imagine if that starting point was there. Maybe I can use that actually. There we go. You can see that vector previewed nicely if we use the device transform as the input there. So that dynamic casting comes into effect once again to enable us to use these different things. So in terms of how we'd go and use this for a drawing application, the first thing that I want to do is create a cursor, a custom cursor. So essentially what we have right now is we have a ray that basically if we point it off into the distance, it's got like an infinite, or not an infinite, I think it goes for about 10 meters, the length of this ray. So we don't actually have control over how long or how far away this ray goes. We're basically going to create a little algorithm that gives us total control over this cursor, which will enable us to go ahead and then draw some curves with a drawing application basically. So I'm going to begin by just treating this as a line output coming out of the track pointers component in Grasshopper. And I'm going to get the endpoints, or start and endpoints of that line using the endpoints component. So just grab that endpoints component from Grasshopper and drop that into the canvas and connect that line up to there. So now what I've got is I've got the starting point and the ending point of my tracked device of that ray in particular. I could then go ahead and I might create a SDL, which is a line with a strength, direction, a starting point, direction, and length. So I'm going to go ahead and drop that onto the canvas. We're essentially going to create a new line using these points. So the start point for this line is just going to be the start point coming out of endpoints. The direction is actually going to use this dynamic casting we were talking about. So we're going to go in the direction of that vector that we were creating. So we're going to input that vector into direction, just like that. And then the length is what's going to enable us to create this kind of customizability in our cursor. So I'm going to make my length 500 millimeters, like that. So now when I press on my device, you'll see I have a much more controlled length in all directions. And I could go ahead and change that length dynamically as if I were drawing something. So I'll leave it as 500, and what I might actually do is synchronize that parameter up to my Fologram device. So I'll send it through to here, and I might call it cursor length, just like that. Unsync and resync just to get that name back up as well. So now we could, go and point with our cursor, or we could dynamically change it so it's a smaller cursor, like that, really easily. And I might preview these previous things off. So just to preview where that cursor is for me inside of our actual mobile phone, I might create a mesh sphere again, the good old mesh sphere, and I'm going to plug in the endpoints of this curve. So I'm going to create another endpoints component. I could actually just copy this one over here, and I'm going to plug that line into there, just like that. And I'm going to make the the endpoint of that component to have a sphere. And of course it doesn't appear on our device just yet, but I'm going to go ahead and sync that guy like this. And I'll right click on that and just make him red. So now on my device, wherever I press, I get this indication as to where my cursor actually is on the screen. And that kind of helps with a bit of depth perception. So if we're further away, we're going to have a smaller cursor. If we're a little bit closer, we're going to have, you know, a larger cursor, just like that. And it just gives it a little bit more control over our drawing application. So I'll give everyone just 2 minutes to get to that point, as you kind of see on my screen. And then once you have got your cursor drawn up, we can get stuck into actually drawing these curves using global variables based on Gwil's explanation a couple of minutes ago. Once again, if you're having any troubles or you want me to repeat something, just jump on the chat and let me know if there's anything you want me to clarify. Okay, cool. So not much life on the chat, which hopefully means everyone's cruising along really nicely, which is hopefully good. So we can keep moving forward with how to build this drawing app. So what we're actually going to be tracking here is basically the endpoint of this cursor that we're doing. So we want our curves that we're going to draw to appear on the screen. Okay, so now I'm seeing a bit of life in the group chat. Okay, so the sphere is not appearing on the screen. Please make sure that you've got the sync object component dropped onto the canvas to get that sphere appearing on your screen, and also make sure that you're working in millimeters. That's another thing just to double check as well. When you say you can't see your line, I mean, it doesn't matter if you can't see your line on your phone. If you want to see your line in Grasshopper, just preview on this component here, line SDL, and you should be able to see your line in Rhino. But it doesn't matter too much if you can't see that line as well. So, like I said, we're going to basically try and create a recording of all of these curve points, these endpoints coming out of this line to track the location of our cursor, and then we're going to turn that into a curve. So one kind of really dumb way to do this, and this isn't the way that we're going to do it, but I just want to demonstrate it as a little bit of a prototype, is we could use a data recorder to track the location. Then we could create a NURBS curve out of that, and then we could synchronize that to our device. So just to demonstrate that working, I could now go and draw a curve inside of my application. But unfortunately, like, whilst this gives me kind of like the output I want, it doesn't really give me much control over what I can do with that data unless I have manually go in and change things. And I certainly don't have the control that I want over I certainly don't have the control that I want over being able to draw multiple curves, for example. So I'm going to go and just delete those guys for now. So I'm seeing a few people are struggling to see their lines and points. So as I said before, it's not about seeing lines and points in here. If you want to see them, you just need to right click on line SEL and go preview on and make sure that your red marker's on. But all you want to see in your device is that red sphere appearing and following as you kind of touch and drag on the screen. So if you've got that, that means you're good to go. So the way that we'd want to go ahead and record these points is to use global variables in the way that kind of Will was explaining before. So I'm going to just drop onto our canvas both a get global variable and a set global variable. And I just want everyone straight away to right click on these globals, and I'm going to call them points, and I'm going to call this one points as well. And what we will do essentially is we're going to send in this endpoint into a merge component. We're going to merge it with basically a group of existing points, then output and re-update the global variable itself. So I'm going to basically create a merge component. So it's this one here that's got like a bunch of lines entwining together on a grasshopper component, like that. And I'm going to merge in the endpoints out of here into that guy, like that. And then I'm going to merge it with this global variable. I'm actually going to get rid of that extra merge option because we just want to. And then I'm going to set the new global variable with those points. So we're basically creating a relationship where we're constantly kind of moving around and creating a new cursor location. Every time we create a new cursor location, we send it to the merge component and merge it with this existing points global variable. Then they both get set out, merged together, and then they set a new points global variable. I might just flatten coming out of that result as well. Ooh, I'm getting a phone call from my grandma there. That's quite funny. Should have told her I was doing a workshop today. So those are going to merge in together, and we're going to get like an updated points value that will then go through and update this. So as we're updating that device location, this is kind of repeating over and over again, and we're getting this kind of like output of global variables. So then rather than using that data recorder output, we could go and copy this global value, which is now going to contain all of our points, and we could create a NURBS curve out of it, plug that into there, and it's going to say that there's insufficient vertices straight away because we don't have any points saved, and we could go and sync that object like that. Cool. So now I'm going to give that a go and see if it works. So if I go and draw my curve, it hasn't worked for me. That's right. So one mistake that I've made that Will didn't make, which he talked about, is that we want to have a dynamic update for this global value. So basically this is only going to update if we press on it straight away, but I want to make that a dynamic update for the value. So I might actually try that one again. So you see my curves actually come through now, but now if I go and draw, I'll be able to get this curve kind of showing. So I've just had a quick thought. If you actually, I'll just let everyone go ahead and build that little application. So we've now got a curve drawing application that's working quite nicely. If you're not able to see the curve that's being drawn, just let me know in the chat if that's what you're talking about. If you don't see the lines that are coming out of your device, that's not a problem. We're only worried about getting this drawn curve to come out of our device. So let me know in the chat if you've got there and it's working nicely with that setup, or if you've got any questions about that, or if you want me to repeat something, and then let me know if something's gone wrong, and just give me a description of exactly what's gone wrong, and I'll try and give you a hand. Yep, so the play button on the global value, it's not just visible. Just right click where that kind of like, input is, and just make sure that you've got dynamic update on. And that'll get your play button appearing nicely. If you're getting the input parameter v failed to collect data error, that's because you haven't actually gone onto your device and tried to draw a curve. So once you have this setup working and you're sending all of these global points into this component, the points will go ahead and input into here. Basically, by default, you won't have any points coming in with that global variable there straight away. All right, cool. It sounds like everyone's kind of just clicking a little bit at the end and solving their own kind of issues, which is good to see. So it's probably like a little kind of thing that's just missing. So hopefully everyone's kind of got to a point where they're able to draw a curve. So right now, what kind of like a little bit of a problem with what we're doing here is we're only able to draw one curve. So if I like ended my curve over here and I tried to draw one over here, you'll see it actually creates a connection to my previous curve over there. And the reason for that is that we haven't really written in anything into our definition that enables us to kind of break these curves up and go and dynamically draw multiple curves. So we're going to try and set up our definition. It's going to get slightly more complicated. So what I'd probably recommend doing is maybe just grouping that one and just moving it to the side, because we're kind of done with this cursor sending points part of our definition, and we're going to start working over on this side. So basically the conditions that we need to meet to be able to draw multiple curves in this scenario are two things. We need to basically create our own global variable for the curves, so we can store a lot of curves, curve data together, which is going to enable us to save out multiple curves as we draw them. And the other thing that we need to meet, the other condition, is we need to empty this point list every single time we're done drawing a curve. So we're basically going to set up a relationship where we, if we draw a curve and then we let go, we update our definition, so we save out that previous curve, empty the points, and then start getting ready to draw another curve again. So let's go and write those conditions. The first condition is that we want to save the curve output to its own global variable. So over here, I'm going to create a new get and set global variable pair, and I'm going to right click on it, and I'm going to call this one curves, and I'm going to do the same with this guy here, curves and curves, like that. And we're going to do another merge. So we're going to merge, I might create a little curve container as well here, just like that. We're going to merge that curve container with this curves global variable, and then we're going to output into curves. So we're basically saving or storing our own curve data. That's not going to do anything right now. Like what you'll see is all it will do is just continue with one curve. So we need to set up a condition that enables us to end the curve as well. The other thing that I said we want to do is we want to empty the point value so we can start a curve again. So I'm going to create a geometry container, a completely empty geometry container. and I am going to input it into a points set global variable like that one. So that'll empty out all of my points like that. So now you'll see I don't actually have my curve because I've updated all of the points in that global variable to be an empty geometry. So I can actually start drawing my curve again like that. So then if I went and updated that again, my curve will disappear because it updates that global variable. Those are the two conditions that we need to meet, but now what we want to do is we want to set up a condition that says once we've finished drawing the curve, do these two things. So the two things we're doing once again is we're updating our collection of curves and saving them to their own global variable, and then we're resetting the points. So what we're going to do is we're going to group all of these guys here, and we're going to use the track state component in conjunction with the state gate to do this kind of like saving trigger. So I'm going to once again just go ahead and go to my tracking components here. So we use this just briefly before the track state component. I'm going to drop it onto the canvas, and we can go and connect our device to that track state component again. And you'll see if we created like a little panel, if we tap, we're going to get press, lost, hold, lost, all of these things. So what we're going to do is we're going to set up a state gate that relates to these little text outputs in the track state component. So I'm going to go to the Fologram tab again, and we're going to grab the state gate, which we learned about yesterday, and we learnt about it in the context of true or false values. But as we know, we're just inputting text values that are going to trigger one of these events. So the state that I want to trigger is actually called release. So release happens when we draw, and then we let go of our device. So in our state gate, I'm going to right click over true, and I'm going to just change the value of true to say release, R-E-L-E-A-S-E, and then I'm going to remove that false value. So zoom right in and you'll get this kind of like dynamic ability to change your component, and I'm going to plug that state into there like that. And then basically you'll see it turns green, blinks very quickly when I let go of my device, or I release the trigger on my device. So that state gate is going to trigger all of this to be true once I'm done with a curve. So I'm going to go and connect that guy to this group here. And now as I draw a curve, you'll see that it goes and releases that trigger. So I draw my curve and it resets like that. Okay? But what it's actually doing now is it's deleting the actual curve itself. So what we want to do, just as one last little thing, is we want to create a get global value global variable, and we just want to make this the curves component, and we're going to right click on it, make sure it's a dynamic update, and then the output of that will basically grab the curve data that gets merged here, and we can go and synchronize that to our geometry. So now what we're doing is we're saving out our curves and storing them over here every single time. So now if I go and draw my curve, it stays there. Oh, it's saved all of them there. That's not good. Hopefully, oh yes, that's right, because it's stored all of my curves. But if I come over here, you'll be able to see it more clearly. I draw a curve and it saves the curve, and I can draw another curve and it saves that curve as well. I can draw another curve and it saves that curve as well. Cool, so I'll just give everyone 2 minutes to get to that point where you're able to draw curves repetitively and let go inside of the Fologram application. And in a second, I'll teach you how to get rid of all of this mess that we've created as well. So let me know in the chat if you've got to that stage okay, or if you need me to re-explain something if you're getting an error, and we'll try and problem solve any of those issues. Hi, Juan. So I see yours aren't saving. Do you want to just make sure that you've got this output set to another dynamic input? So just make sure that that's definitely dynamic, and then hopefully that saves it. Make sure that you have release typed correctly, because that's type sensitive as well, and you'll need it to be set to release. And you'll need these guys grouped, and then this connecting to the whole group, not just one of the components. So I'll zoom in a little bit closer just so everyone can have a quicker look. So just be aware, dynamic updating here and dynamic updating here. We don't have dynamic updating in this one, so leave that one as not dynamic, and otherwise that creates an infinite loop. So just check that you've got those dynamic updates even if you've got my exact components. Also just make sure that your track state is connected to the devices. I mean, if you want to make it even a little bit more obvious, we could actually just do a new connected devices here, and that'll do the same thing. So let me know if that works for you. Awesome, I'm glad most people have got there, because it's a little bit of a complicated logic to go and save these things, but I think Gwil's explanation's been helpful. So that's really good to see that most people are getting there. I mean, if yours isn't saving one, maybe it has something to do with this part of the definition being slightly incorrect. So let me know if you were able to draw the curves okay previously. The other thing I think Will also mentioned in the chat is that you need to make sure that you've got a nice kind of well-lit space with good tracking so the device is able to clearly track its location as well. One last thing that you could try that could maybe help you out is just change this curves output to a mesh pipe geometry like this. And maybe you could give it like a radius of, I don't know, 5 or something. And then you could plug that in. It might be like a little bug in the, or it might be like a scale issue that you're having as well, like with the curve radius. So if you want to just try the mesh pipe component in utilities, you could plug your curves into there and send them. Like you see, I get squiggly mesh pipes, and I can draw mesh pipes now as opposed to just that curve. So maybe just check if that makes it work for you as well. The other thing that would be good to just check is if you think it's not saving, just double check that out of your global variable you're getting a list of curves every time that you release your component. So that would be the last thing I'd just quickly try. So most people seem to have got it working nicely. Now, just in this little drawing application, yeah, recursive loop detected. So Shirley, as I mentioned, don't set this one to dynamic update. Make sure that that curves is not set to dynamic update, okay? Cool, yeah, okay, so maybe I'll clarify that one as well. So anyone else who's having problems, please make sure that you get the names of your global variables correct. So the last one here, you just need to make sure that's curves, because it forms a relationship between all of these global variables over here. If that's not set, then you won't have that relationship as well. But yes, like I said, don't set this one to dynamic update, but set all of the other ones. Don't set that one either. We don't want that one as dynamic update. We want this one as dynamic update and this one as dynamic update. Maybe I'll do a little group and I'll make them a little blob. Oh, bifocals changes that. Yeah, it does. I'll make them like a nice kind of red color or something. No, it's not letting me do it because of this plugin I've installed. That's a bit annoying. Oh no, it does. Cool. I'll make it red so it's obvious which ones we need to have dynamic updating to. Blob, and then that guy up there like that. Cool. So the red ones that I've got need to be dynamic updates. All the other ones are not dynamic updates. Cool. So the last thing we want to do, like I said, is to reset all these curves. So to reset them, generally what you do is you just do what I did with the points over here, and we can create an empty geometry container and input that into a global variable called curves. So I could go and get a set global value and say curves, and plug that into there, and that'll get rid of all those curves straight away. But that doesn't help me here again, because now I've got all of these curves that I'm drawing, and then to reset them I'd have to go back into Grasshopper and update that global variable. So what we can do is we can use the state gate once again in a similar vein to what we used it with yesterday. We're going to use it with a button, and I'm going to rename this button reset like that and synchronize it. So I'm going to plug that button into the state gate, and of course our button is just going to give us, true or false output. So if I click on it, true, false. So true when pressed, false when not pressed. We don't actually need the false output, so I'm going to zoom in and get rid of it as well. Basically, on true, we're going to trigger this event. So I'm going to just group those guys, and then connect that state gate up to this. So then if I'm inside of my definition, just get the end of that out, and I'm drawing these curves, draw multiple just for this demonstration, I could go ahead straight from my device and reset it, and then I could start drawing curves again just like that. So if you got there, well, just a little bit of kind of clarification. We're just going to have a quick 5-minute break so everyone could go, stretch their legs or have a coffee. But if you got there, it'd be great if you could spend maybe like a couple of minutes finding a little object, like an interesting object nearby, and just trying to trace it. So for example, I've got this little plant here, and I might go ahead, I'll just reset my curves. I might go ahead and try and trace that guy. Ooh, one thing that's missing for me is this sync object component. I know it is there when I press, isn't it? So I might go and try and trace this little plant here, like that, like that, like that. So it'd be good if everyone could just have a quick go at maybe trying to digitize an object in their physical world, like in the room you're sitting in, and then you'll get that data sent back to Rhino, so you have like a little kind of digitized version of whatever it is. So it's almost like sketching in 3D is what the application we've created is. So I want everyone just to quickly digitize some kind of object, because we're going to go ahead and use that data for a little design task after this quick 5-minute break. Once again, if you had any issues, just let me know in the group chat, and I'll try and help you all with some problem solving and some advice. And if there's any concepts or things you want me to re-explain, please let me know as well, and I can go over a couple of things really quickly. But let's reconvene in 5 minutes or so, and then we'll get into the next part of this workshop. Yep, so I'll quickly talk about how those curves are being reset. So I can redo this again. Basically, as kind of Gwill explained, whenever you have a global variable, so in this instance we have these curves, we've basically created a list of curves inside of this data. But whenever we input something else into that that global variable, we can actually override the data in that. So if I go and create, you know, a global variable where I'm going to set a global variable, I'm going to call it curves. I could go and, you know, perhaps create a mesh sphere in this. And if I input that into curves, you'll actually see that my curves gets overridden to a mesh itself. So the global variable, despite the fact being called curves, that's just a name, it just takes in the most recently updated data for a set global variable. In this instance, when we have, you know, that group of curves, say if we want to reset them, we could just give it an empty geometry container, which has nothing in it, and update that, and it just gives us an empty list. But basically what we want to do is create a little trigger for this inside of Grasshopper. So that's why we're going to use the state gate component. Whenever the state gate reads a true value, we're going to basically wipe out all of the values in the curves global variable. So I'll connect that up to here, and I'm just going to create a button called reset, and that connects to the state gate. I'm going to synchronize it up, so whenever I go and draw curves on my device, I can go to reset, and that'll just trigger that little event, which basically updates that global variable to have no geometry in it. Cool, I'm just reading through a couple of other quick comments. Yeah, so Chigu, just check what Nishant is saying, that all of your global variables are labeled correctly. So we obviously have in here a points global variable, make sure it's named as points. We have two curves ones, because this part here is updating the curve global variables, but over here we want to reset that points global variable. So that's probably what's causing your problem with not being able to get that break between the curves. You need to reset those points value, because they're coming back into here and giving the data that draws the next curve. So if you don't update that value, you're actually taking all of the old points from the last curve and putting them into the new curve, which means that you don't get that break between the two curves to create an entirely new curve. Yep, so path, I'm guessing, I mean, it sounds like to me, I can't be too entirely certain, but do you have your sync object component turned on? It sounds like what you're doing in that scenario is your, you don't have your sync object component on immediately, so maybe just check that you've got that on before we move forward. Because it looks like if you're saying that you're able to draw the curves and they will appear in Rhino, it sounds like there's something going on here where the sync object component's not working. Maybe just try plugging it in, or try, it could be like a visibility issue to do with your units. You could try doing that little mesh pipe trick that I was just saying before and plugging that into there. So then when you draw a curve, you get a mesh pipe kind of as the preview rather than the curve itself. Then, you know, if you could have like a radius that's a little bit higher and have some thicker, you know, geometry that you're drawing there, like that. I'll upload the Grasshopper file at the end of the class. I mean, actually, I probably could just put it on the forum. I'll put it under interactive rod bending design, just really quickly. So I've just posted my definition on that interactive rod bending post just here. So if you want to grab it, if yours isn't quite working, and just double check with yours where maybe you've got like a little bit of an issue, just go and check that one out and you should be able to just use mine easily. Cool. So that's been, I think, well over 5 minutes. So hopefully everyone's got to a point where they're able to draw curves with an interactive app. And hopefully you've gone and traced an object. I've traced a tree because I find, or a plant because I find them kind of a bit more interesting than like a box or something. But I'd highly recommend maybe a more organic shape would be a good thing to just quickly trace. But you could also do that in your own time as well. So what we'll do now is I want everyone to go and open up the rod bending template file. So this one here that I asked you guys to download earlier. So it's on that same link. So I'm going to go File, Open, and we'll open that rod bending template file straight away. And let me know if you have any issues with the components straight off the bat, because obviously we had that issue yesterday with, what was it, tree sloth or something. But I think this one's good. I did check it out just to make sure. I think you should be okay with this definition. So if anyone could just open that and tell me in the chat if they got any like plugin errors or something, but I think it's pretty much just made from Fologram components and Rhino only components, so you shouldn't get any issues, I don't think. Alright, so no one's saying anything in the chat, so I'm just going to assume that everyone was able to open the rod bending template file. Okay, so obviously let me know if you can't, but I think I'll just assume that everyone's been able to do it without any huge issues, which is good. There's a curve offset file when I open the file, but everything else works fine. I'm guessing you mean the error. Don't worry about that error. That's curve offset failed is what you meant. Yeah, that's fine, that error. I've got the error too, so don't worry about it. Basically what it is, it's like one of these little rods has got too small a radius, but that's not an issue at all. We can work through that. I'm guessing it's like this little piece here that's missing or something. Cool, so everything else should work okay. Basically what this file does is it's a little bit of an indication of some of the rod bending projects that we've done at Fologram previously with these kind of like little rod pieces. So what we're going to do is we're actually going to apply the drawing application to this little algorithm here. So the drawing application could be used for lots of different use cases. It could be used as like a markup objects in 3D space tool where you want to like quickly write little notes or something. You could use it to digitize physical objects like I was doing with the plant, or you could just use it as a design drawing tool. So we're just going to use it to facilitate our design a little bit right now. But what we're going to try and do is basically create these little kind of Voronoi-like aggregations through these objects in physical space. So I'm going to once again, I'm going to trace my plant to create this, found object in digital space. And then we're going to basically create like a little Voronoi steel bent sculpture based on that plant geometry as well. So the first thing I want everyone to do, actually no, I'll just explain the definition first. So what the definition is doing is it's taking in a little curve here, and it's creating a bunch of points along that curve, just like that. And then it's actually mixing them inside this big kind of like point cloud. And within that, you create like a little Voronoi thing. So if you've used Grasshopper before, you've probably used the Voronoi component. I personally don't like the Voronoi component, but I think it's a good way for us to just demonstrate this task. And then I'm just splitting that out, so you just find the Voronois that attribute to that curve itself. So we create like a little Voronoi version of our traced curve. That then basically just, we take the face edges of each, we take the edges of each face on these Voronois, and we just go ahead and kind of give them a little bit of an offset, just inwards like that. Then we're also kind of filleting the corners a little bit, so you get these nice filleted edges, in there. And then we're basically just creating this piped geometry that gets sent to this mesh output. And what Gwil's going to do at the end of today's session is he's going to demonstrate like the basics of how you might fabricate something like this. So that would be, you know, taking one of these parts, these little kind of rod bent elements, and basically applying a hologram over a bar bender, like a manual bar bender, and then bending it based on the hologram that you see through your device in the HoloLens or your mobile phone. So what we want to do is we just want to basically first create a little design application that's going to enable us to draw these little Voronoi aggregations. I'm going to come to the end of the definition, so everyone just go to the end of the definition here, and let's just send that geometry to our device first. So I'm going to create a sync object component, send that geometry, and you'll see in my device I get this little kind of Voronoi sculpture. Maybe I'll go and place it over here or something. So there it is there in my device. It actually looks way better on AR than it does on Rhino screen, actually. Much more impressive, I think. Less of a Voronoi it looks like, which is good. So everyone just go and synchronize that geometry to their device straight away. One thing, I'll just reminder, just in case anyone didn't do it for the last one, I'm working in millimeters, so you might have issues if you're not, using millimeters as your Rhino units here. And then what we're going to do is really simple. So once you've synchronized that object over here, I just want you to go back into the curve drawing application and copy everything. And then just go ahead and paste it over here. And just move it out of the way there. And all we're going to do, I'm just get rid of that guy because we don't need that. All we're going to do is put your definition to the side here. And I'm just going to override this curve with this sync object component. Like that. And then that'll disappear. And now I'm able to go and, draw some curves that will turn into the, Voronoi aggregation, just like that. Cool. And then of course we've got our reset button, so we can easily go and reset the whole thing. So I might go ahead and snap to this QR code here. So I'm aligning it to physical space. And once again I could start going ahead and drawing my curves here over this plant and digitizing this plant as a little bit of like a Voronoi thing. Well, I've lost a bit of tracking because the sunlight's giving my phone a bit of a pain, like that. And then we could create a nicely digitized version of this plant geometry that I've got here. So I want to give everyone just 5 minutes to give that a go. So basically all I did, I'll just re-demonstrate it once again. I didn't do anything fancy at all. I basically just went into our curve drawing application, copied everything, and then pasted it over here. And of course I want to get rid of that one because that was just my little demo. And I'm just plugging that into my curves, like that. And I'm getting, this little Voronoi kind of metal bent aggregation on my screen. So I'll give everyone, like I said, just 5 minutes to have a quick play around with that, and let me know in the chat if it worked for you. I'd love to hear if it's working well. So just give me some reassurance, that'd be really good. And then we'll have a quick discussion, and I think Will's going to take over and demonstrate potentially the fabrication process as to how you'd go about making this thing with like a holographic overlay on a bar bender. So Anya, so you getting the Voronoi overlay inside of Rhino? That would be my first question. Yeah, so one thing I forgot to mention, make sure you draw inside of the box. So the way the definition works is you need to draw within inside of the white box. I forgot to mention that one. So just make sure that you're drawn inside of the white box. So that's why I was kind of like aligning to the QR code marker next to the plant so that the plant would actually fit within the box. So you can kind of see in mine, the box is just there. So you want to draw your curves inside of the box. Sorry, I should have mentioned that one. So if you're not seeing the Voronoi overlay, it's A, because you haven't created a sync object at the end, or B, because you're not drawing in the box. So I'll draw over here. I can draw a curve and nothing's going to happen because my curve is not inside of the box, as you can kind of see there. Yeah, I can recap that for you. Really, really simple. So basically, I'm going to delete everything that I put in here. So all you have here in our definition at the start is a little purple kind of curve input, okay? So what I'm going to do is I'm going to jump out to our curve drawing application, and I'm just going to delete this because that's what everyone else actually has. And then we just copy everything, Control C, swap over to our definition, Control V, and all I'm doing is I'm just grabbing this get global variable sync object, which has all of our curves, plugging that into here. So it's basically like the end of this kind of little definition, which is here, the collection of all our curves. We're just plugging into the curve input here, so you can go and do this kind of little Voronoi steel bending drawing exercise. Yeah, so there won't be any output from the raise data. So as I kind of mentioned before, the raise, like they are a tracking component. So you actually have to signal something to draw with raise, basically. So in order to draw, like in order to use the raise component, if I were to kind of like demonstrate it again, you need to have a connected device, then you need to have a track, pointers, and of course nothing's going to come out. Like if I put a panel here, nothing comes out until I actually, do something on my phone. So now I'm touching my phone. When I let go, nothing's happening. When I touch, it starts again, and you can kind of see that ray I'm drawing. So you have to actually touch it to create the ray. What you could do is, No, you couldn't use the track scan component to map. Basically, the box is there to create the Voronoi algorithm. You could change the box so it's in a different position if you wanted to, but basically the best way to do the algorithm is to keep that box so it enables that Voronoi simulation to happen. So basically, like, this is the underlying geometry of that whole thing, and we're just taking out a small part of it based on where our curves are. Yeah, I agree. If you're a Mac user, you should probably buy a PC. I had a Mac a while ago, but it's quite incompatible with everything. Cool. So one last thing I might just quickly touch on, because there's like a tracking component that I didn't go through, and we're going to go through it in a bit more depth tomorrow. But the tracking component called track markers, which you can find here, enables you to track things like QR code markers, like little mini ones like this, or things called Aruco markers that look something like this. So tomorrow we're going to look at how to use this component for the carving exercise. And there was a file that I wanted you guys to download from the interactive rod bending forum post that I put up called Fologram Markers 4x4. And I promise you I've got the right printing file for this today, but if you could just go and print one of these pages off, I know it's a long document, just maybe print off the first page and just cut out one of these Aruco markers. So you have one of the Aruco markers. That'd be really great because we're going to learn how to use them in a fabrication context tomorrow as well. So I'm going to hand over to Gwil now, and Gwil's going to take you through the rest of the workshop. So if you've got any other questions or you had any other issues, jump on the forum and get in touch with me. Otherwise, I hope that was interesting and you got a bit out of it and get a bit more of an understanding of how you can use the tracking tools within Fologram to go and create and digitize things in the physical world. Cool, thanks guys.
Okay, looks like we've got a good switch over, which is always nice. So Sean has shown you a couple of the tracking components in Grasshopper, as well as given a kind of a practical use case for global variables, and it seems like a few of you have been following along with that, which is excellent. But this workshop's really interested in the next step. It's how you might begin to build mixed reality applications that are specifically going to help you with complex fabrication problems. And a lot of the projects that we've done at Fologram, especially early on when we were first trying to understand what was possible in mixed reality, we're working with kind of linear stock material, like a steel bar and steel rod, and trying to find ways to form that material into really complex three-dimensional shapes. And so we began building mixed reality applications that would assist really specifically with rod bending. It's the classic project which is doable with a robot. Like, it's very easy to bend rods using CNC bending machines or with robotic arms. So making parts is easy, but assembling those parts is exceptionally difficult, and we thought there was a big opportunity to not only kind of cut out this expensive robot from the part fabrication, but also from the assembly of these kinds of structures. So another thing actually that comes to mind really quickly, and I might just give me a second. So typically we're using the HoloLens for doing this kind of fabrication, but not always. So I'm just going to try and find, yeah, here we go, awesome. So we did have some people use Fologram and the mobile phone to do some rod bent fabrication. So it's not like it's impossible to use these sorts of applications to fabricate things even if you don't have access to a HoloLens. So this is a really fantastic project by a fab lab in Tehran. They did a workshop from bent recycled steel called the Nodeless Network. And it might be worth having a quick squiz at this because, or a quick look at this, sorry, I don't want to use Australian jargon too much, because it might give you some ideas for what you could do with kind of access to similarly low-tech tools, just like mobile phones and cheap benders and things like that. Okay, so for the next half hour or so, I'll try to explain the thinking that went into how to develop these bending applications for you all, as well as together we'll build a simple mixed reality bending app so that you understand what's involved. I mean, the one that we used in our built projects is more complex than what I'll show you today, but I mean, we were developing it to do a very specific kind of bending with a specific kind of bender. So I don't think it makes too much sense to show you a specific application. Instead, today I'll just show you something generic, and then you're free to go and adapt and extend that on your own if you use it for a project. Okay, so the challenge here is to build a tool that will let us fabricate these kinds of objects that, in this case it's kind of 3D cellular geometry that Sean was showing you earlier. These forms are made up of planar faces, so it's not like these couldn't be fairly easily constructed just from templates. But the definition that I'll show you, or that we'll build together today, you could use it to build three-dimensional shapes as well. So we're going to work from 2D shapes, but the definition will also work with 3D rod aggregations. Now the logic behind the definition is actually pretty simple. It's like it uses a clever trick, and to understand the clever trick and the logic, I guess first it's worth kind of thinking through what we're actually trying to do here. So I'll try to sketch in Grasshopper for this. So we have a component, that's our part, and we have a bender somewhere, so I'm going to just mark out a kind of a little X. That's our bender. We've got a bending arm. We're going to have some sheet material or some stock material, so this is our part, and the bending arm is going to bend that part by some amount around the bender radius. And what we want to do is we want to set up a hologram that shows us exactly what angle we need to bend that part to. Now the other thing is that in plan that's all pretty simple, and if we're just working with 2D parts, that's not overly complex. But if we think about this in elevation as well, so let's say here's our bender, that's our bending axis here, this cross, we've got our part. Now what if we're bending a 3D bend? So let's say our part might actually be starting off, there might be a bend here already somewhere, and we need to bend that around that axis there, which is what we would need to do if we were going to bend, some of the bends in this part here. They're not actually two-dimensional bends. I mean, each bend is in a plane, but it ends up forming a three-dimensional part. So we need to set up a parametric model which lets us position our part geometry in some known location relative to a bender and show us the bend angle that we need in order to bend it. Hopefully that makes sense as a kind of as an intention. So there's a few kind of elements to that. So maybe we'll start by, we'll build a few different definitions, I think, that approach it in a few different ways. So let's say we've got a part here. This is one of the faces from my big object, which we'll come back to in a second. I'm going to reference this one curve into Grasshopper, and let's in Rhino, I might just model roughly where my bender's going to go. Hang on, let's just... I'm not going to do this to any kind of scale. We're just going to... because this is all just diagrammatic, we're not working with a real bender. So let's say that's our approximate bending geometry there. So what we would want to do is we would want to orient our part onto this thing so that we have some way of understanding, okay, what is my bend angle, right? So we need to orient each corner of our curve onto this bender in some way. We need to show the shape of the part before the bend and the shape of the part after the bend. So that's essentially the challenge here. The other thing is that for this part here, we're going to be bending it from just a straight piece of material initially. And we're going to be bending, again, I'm just drawing some diagrams here. We'll do the first bend, which might then make our part look like this. And then we'll do the second bend, which might make our part look like that. And then we'll do the third bend, which might make our part look like short bend, etc. So we're going to be gradually forming this shape, and we'll always have a straight section of remaining material. So what our bending application really needs to show us is three things. We need to know how long this bent segment is. We need to know what the bend angle is. And we need to know if there's any 3D rotation of the part. So whether we're bending it flat or whether we're bending it in some other plane. Okay. So if we were doing this in Rhino, we could work it out just slowly on our own, right? You could just model it. So we've got let's say we want to fabricate this part here. We could go, okay, well, what's the length? And in this case, I don't have any scale in this model. It's 145.44 millimeters. So it's a teeny weeny part. Maybe let's scale this up so we've got some scale. Let's make it way longer than that, 5 times longer. Okay, so now it's about 700 mil long, my part. So I could go, okay, well, the first thing I need to do is I need to orient a straight piece of material that's 700 mil long from the start of my bender. I might make this thing a bit bigger. This is going to be my bender radius. Right, so again, just to explain the logic. So I've got a 727 mil long part. There it is there. And then let's say the first bend I'm going to do is this bend here. So I might check, okay, well, how long is that bend? From there to there, it's 111 millimeters. So I might move this 111 millimeters that way. So now I know, okay, I've got my length right. I have my remaining stock material for my part. The last thing that I need to know is where I'm bending this around to. And so then I would need to measure the angle between these two things. And this is where it all gets a bit complicated. So if we were doing this in Rhino, again, just so you fully understand the kind of the logic or the problem, we might do an orient 3-point. So this would be reference point 1, reference point 2, I think, reference point 3, let's try that, and then my target would be 1, 2, and 3. And then we need to mirror that. And then that's showing me my bend angle. So for every single bend in the part, these are essentially the steps that we need to parametrically go through and produce. And there's a little bit more complexity here as well because, our bender is going to introduce a fillet into this part as we bend it around this bending radius, the bending block. So we would want to take that into account as well. But that essentially would give us enough information to go by. If we had a really small bending radius, then you're essentially going to have a really tiny fillet, right? And so this begins to approach what we might expect the actual holographic instructions to look like. So does that make sense to everybody so far? Just give us a heads up in the chat in terms of what we're trying to work out how to do with this little application. I guess there's a bit of a delay in the live stream. There's maybe like 60 seconds or so. So we've got one. I've just seen one person come through. Sort of makes sense. If you want to see more examples of how this bending works, there's a few videos of it on vimeo.com/Fologram, and I think I showed one or two briefly in the lecture the day before yesterday. So you can also check those out. All right, so we've now got roughly a sense of how this bending works just by going through it in Rhino. So we've defined what the problem is. So now let's have a crack at rebuilding this same tool parametrically. And we'll just do it with one part to begin with. So we're going to use this curve here. So if you're following along, just draw a polyline. Make sure the polyline is roughly 1 meter long, and you're working in millimeters. And if you want, that polyline can be in 3D. Your polyline can really look however you want. The idea is to make a tool that's sort of flexible. Any kind of 3D shape is going to do. Okay, so if we've got it, once you've got a polyline drawn, we're going to reference that into Grasshopper, just using a curve component. And we're going to get straight into the tricks, which is good. So the way that we can easily orient this part onto our bender per bend, so for each kink in the polyline, we orient our part on, and also we want to orient it in the bend plane. There's tons of ways we could do that in Grasshopper. You could go through and break the curve up into its different points and then build planes from those points. You could go through and find like perpendicular frames of discontinuity, work it out from there. The easiest way that we came up with doing this is to fillet the curve. So you use a fillet component and define the bender radius. So let's make up a bender radius here. Maybe our bender radius is like, it's pretty small for these small parts. Maybe it's around 25 or so. We can make it a bit bigger, maybe 40. And so this, as Sean would have shown you before with the filleting of those curves, this actually shows you what the part is more likely to look like after it's been bent, because the bender typically introduces a fillet into each one of into the part. So we get this filleted version of the curve, and then we can explode this curve to get the individual segments. So we end up with straight line segments and fillets, right? Which is kind of nice. And we can use this information to orient our curves. Now, each bend is effectively going to be a combination of a straight line segment and a fillet, right? So if we're doing this first bend, we're going to have this amount of material sticking out straight from our bender, right? And then we're going to see the bend afterwards. So I might just bake this so you can show it. I'll show you exactly what I mean in Rhino. I'm going to orient it onto our bender as well. 1, 2, 3. 1, 2, 3. Let's rotate that around. Actually want to put that there. So that's going to be after our bend. And just to give you a quick idea, that's what it looked like before the bend, right? So we're going to bend from straight around some bending radius to that bend there. I'm going to go through and delete all this stuff. Now, because we've got our fillet radius, let's also get rid of my Rhino model. I can actually bend. Excuse my dog, by the way. He's very upset that he's being left upstairs while we're live streaming. I'm going to make a quick parametric model of our bender so we can actually see what's going on a little bit better. Okay, there's our bender. And to simplify things later on, I'm going to move this bender preview just over a little bit so that rather than the bender being centered, oh, actually no, I'll leave it there, it's fine. So this is our bender radius, right? So we've got our part, we've got our bender preview, and the next step is to orient this part onto this bender, one bend at a time. Now we can do this the really simple way first, and then we'll gradually introduce a bit more complexity to make it more like the actual bending application. So the simple way is to go through and just try to convert all of these line segments or curve segments to arcs. So I can do that by using a circular arc parameter component and just plugging it straight in there. And what that does is, if we have a look at what's in there, if it can convert this curve segment into an arc, it does. And if it can't, it just ignores it. So it can't convert a straight line segment into an arc. With the other ones, it can. So this is a really nice, quick way of checking, like, do we have an arc or do we have a line? Which is the other thing that we can do. So this gives us the line segments. This gives us the arc segments. So as a really kind of dumb demo, what we can do is with the arc, we can deconstruct the arc into a base plane, a radius, and an angle domain of the arc. So let's plug that in. And actually before we do, I'll clean up the tree so we can just get rid of all of the null values in that list. So we've only got the arcs. So this gives us the planes of the arcs. My plane preview is really tiny. I'll just make that a bit bigger. Where is it? Display. Preview plane size. Let's make them 50. Let's make them 10. So very conveniently, we're now getting these planes with the center of the arcs. One for each bend. Super duper useful. And what we can do is we can orient our component, so our filleted geometry, using the reference plane of the arc as our initial plane. And because I made my bender at XY, like just at the origin, we can leave the target plane as default. So now you can see that part aligned such that every single bend is nice and flat over our bender. That's not necessarily useful enough holographic information yet. but it's a pretty good start. So what we want to do is we want to be able to step through these bends one by one. So let's use a list item component to grab the, let's go 0 less than 10, to grab the bend that we want. And this will let us just orient the bend on one at a time. So you can imagine as we start building this holographic app, we can change this, we call this bend. We could synchronize that, and then on our phone or on the HoloLens, we're able to step through and pick the bend that we want. Okay, so next step is to make sure that these bends are actually oriented properly. So for now, what we have is we're taking the start point of the arc. You can see it's aligned here, end point of the arc. And I'm pretty sure the x-axis, I can't remember if the x-axis is always actually aligned to the start of the arc or not. But what we'd like to do is to make sure that in fact, let's see, what we want to show. Yeah, I think this is always going to be pointing straight down. Yeah. Yep, okay. So what we want to show here is, and we'll just build the most simple version of this bending app as we can first of all. So the holographic information isn't going to be perfect. It's not going to be the same as some of the examples on our Vimeo page or whatever. But what we have here is we know what this straight segment at the end of our bend looks like now. We know that. Jump. And we know our bend angle, so that's coming around here until it stops. It just looks like that first one just happened to be pretty close to 90 degrees. And then we have all of the rest of the part. That's not enough information to bend this piece yet, necessarily. What would be really useful is if we had the length, like a straight line segment, coming out from the other end of the bender, so that we could line that length of material up with the bend and bend it around until it matched this geometry here. So there's a few different ways to do that, but what I might do is I'll just give you guys 5 minutes or so to catch up with this, and I'm also going to go make sure my dog is quiet, and then... Hi everyone. Okay, I've just gotten told that apparently the stream dropped before I explained what I was doing. Just wanted to take a quick break to go and calm the doggo down. He seems to be calm now. He can hear me talking downstairs, and so he gets very excited and wonders why I'm not playing with him all the time. But yeah, apologies for that. We're now back on. Unfortunately, it seems like we've lost the audience because of that, though. Well, for the lucky few who are still here, we can keep trudging through this. Otherwise, I'll upload the definition and it'll be on the community forum to go through. Okay, so where we left off, just so I could calm the dog down, as you notice, we now have no barking, is we've got a way of orienting our part onto our bender. We can preview the fillet radius, which is really nice, but this isn't actually necessarily giving us all of the information from that diagram that I sketched out initially, which is showing us things like the length of the part that, or segment of the part that has to be bent, the remaining length, and the bend angle. Also, we want to show the geometry before and after the bend. So one way to improve this little parametric bending tool, even though what we have here is pretty useful. Like you could probably hack your way into using this to bend parts if you wanted to. What we're going to do is we're going to break up our list of segments into chunks of a bend and the remaining segment. So how we're going to use that, how we're going to do that is using, oh, he's back, the split list component. So I'm going to take my segments, connect them up there, and then we're going to have a splitting index, and that's going to be our bend multiplied by 2. And that's just because we want to be choosing 2 segments at a time. So for each bend, we're going to be picking 2 of these segments. Okay, so now we have our split index. I'm just going to move this stuff over. And if we have a look at that with a curve component, bend 0, we've got nothing now. This is going to start from 1. So bend 1, we have our bend and the straight line segment. For bend 2, we have this bend and the straight lines, like the remaining part. This is going to be much more useful for us with actually creating a bending definition. So what we'll do is for each bend, what we want to do is we want to grab the arc, which I believe is always going to be the last curve in this list of curves. So let's go list item. And we'll reverse that list to grab just that last arc. So that we now have the arc. And let's use that in our deconstruct arc component instead. And we don't have the list item anymore. We've just got our arc. So as we step through, this will give us the bend plane, and it'll also give us the entire shape of the component that we will have bent. Now conveniently, what we also get is the other end of the component, and this hasn't been bent yet. And we need this because this is going to tell us the remaining length of stock material, so we'll be able to make a hologram that's just a straight line essentially, showing us that stock, which would make it really easy to line this up and bend it. So for the remainder, and I'm going to call this, name these curves so we can find them. For the remainder, let's just get the length of that, add up the length, and then we'll know how much material we've got left over. And we're going to use that in a second. In fact, yeah, we'll use it in a second. So we've got our part. What we want to do now is we want to orient only this piece of geometry that is going to be bent. So that's these curves here. So they're going to get oriented, and our reference plane is going to be our plane there, and so now there they are, aligned nicely to our model. Now to make this a little bit easier, we now want, what we want to do is we want to show some slightly different information. So I want to align this bend. Let's say I want to align it so that our straight, like our remaining material, is going to come down, show up here, then we'll have a straight line segment, and then we're going to bend around this direction. So at the moment, our remaining material is coming out here. We're bending in some arbitrary angle there and around this way. So that's not necessarily what we want. To make that work a little bit better, what I can do is I can align this plane so that the x-axis is pointing at the start of the bend. Alright, so let's do that. We're going to get the end points of the arc. So that's those 2 points there. In fact, does that component give us the end points? No, it doesn't. Good. And then I'm going to align plane. Take that plane, and the direction that I want to align it in is a vector from my plane to the end point of the arc. So now I've gone and aligned my plane, so we have the start of the bend there. And let's try using that as my target plane instead. Okay, cool. So what we now have is, no matter what our bend is, the start of the bend is always going to be starting perfectly on this x-axis. And that'll be a little bit easier to see if I hide my bender. There we go there. So this is a known point, and that's useful because it means that I can now draw a straight line from that known point to show us the remainder of our stock material, and I can draw a straight line in this direction that shows us the shape of our part before the bend, which is going to be fun. Or actually, I'm not going to draw a straight line, I'm going to do something slightly different, but you'll see how this works in a second. So we can turn our bend preview back on for a sec. So we're trying to show our stock material, the remainder of the length of rod before the bend. We know how long this is. We know where we want to draw the stock material from. So I'm going to make a line SDL. Now the start point of the line is going to be, just so that we can move this around, that's where our bender is. I'm going to deconstruct that plane. I'm going to move the origin in the x-axis by our bender radius. Okay, so now I have my point, which is where my stock material is going to go. So that's going to be our start material. Then our x direction is the bend axis, the y-axis, that's that direction, and then the length of our line is the length of our remainder of material. So there we go, that's basically what our rod is going to look like before the bend. So now we're really getting somewhere. So as I change this bend, you can see far more useful, right? We're seeing our stock material get shorter and shorter. Maybe I'll hide this junk so that we can see this more easily. So as we step through our bends, there's our first bend, our second bend, our third bend, our fourth bend, right? So we know what the end state of the bend is, and all we need now is the start state of the bend, right? So we know the angle that we're going to bend it to, but we don't necessarily know what the part looks like before we bend it. And so that's the next little slightly tricky thing that we're going to need to work out how to do. So the part before the bend is actually not too difficult to work out, right? It's just this exact same part that has been rotated by the bend amount. So we want to get this part here and we want to orient it just straight. So that's the next challenge to work out. You've got to apologize for my messy definition. I'm just making things up as we go here. So we're going to pull that over. So this is our bend afterwards. So we can rotate this part. That's pretty easy to get it to be straight. And then we can move it in the negative y-axis by the length of the bend, which should give us pretty much the right shape, I'm pretty sure. So we know what our bend... well, actually, another thing we could probably do, just thinking about this, is we could probably align our part with the start of the bend as well. That might work. I'll just try that, otherwise we'll do it the other way. Okay, well, that's definitely easier. Let's just do that. So there's two options really for this. One option would be to rotate the part. So we're rotating around or in this bender plane to pull it back so that it lines up straight with our stock material. So that would show us the shape before and after the bend. The other option is this idea that I just came up with then, which is to align our bending plane rather than being with the end of the bend, which rotates it around like this. We align it with the start of the arc, which makes a different orientation plane and places our component at the start of the bend on our bender. So that seems like a more elegant way of doing it, I think. So now we have the start of the bend, and we have the end of the bend. Let's just go through and check what that looks like. Yeah, that's good. I think it's still actually slightly incorrect, and that's because when we're orienting this part, we're orienting it such that the bending arc now, if I hide this thing, yeah, you can see it there. The bending arc has been pulled around here. So this is not actually correct. If we bent this straight segment around, we would lose this amount of material. We would bend this pipe around and end up around here somewhere. And that's because we've rotated the piece around this axis with this radius, and so we've lost this amount of material. So the one other thing that we need, well, there's a couple of other things we need to do if we really want to get this perfect. First of all, we don't want to orient this line segment, and second of all, we want to move our part in this negative x-axis by the length of the bend, and then we really will have a perfect representation of the bends before and after the part. So let's go ahead and have a crack at doing that as well. The simple thing to do is to just move it, right? So we can always do the simple thing first. So we just move and get rid of that. Our object in the y-axis of our bend plane, or negative y-axis, sorry. Actually, let's not use negative, let's reverse it. And the distance that we want to move it is the length of our arc. So this gives us radians, that's not very good. We want to measure the actual length of the curve. So now we have a move vector, and we can just move that, and that shows us the true position of that piece before and after the bend. So this should be more like what each part will look like. Though you can see that this, let's hide this junk so it actually looks right. But this arc here is super distracting. Okay, so we've now got the right shape, like that will bend around to this angle, but that initial arc is kind of irritating. So the last step is to get rid of that initial arc, and then we're good to go with our bending definition, and we can hook it up to a part selector, and then we're pretty much finished. So we're orienting at the moment, we're orienting all of our part. And so all I want to do is to get rid of that last arc in the part. So all I'm going to do is use a shift list component, and I'm going to turn off wrap. And let's make sure we shift it by -1 to remove the last item in the list. And then that's what we'll orient here. Okay, so completes our bending definition. We have the end of our bend, we have the start of our bend. We're able to step through and preview each one of these bends. We can see the remaining material. And this works in 3D. So the bend is always in the correct plane, but you sometimes need to rotate the part in 3D to get it to do 3D bends. So this is where this becomes really, really useful as a holographic tool, because you aren't always bending flat parts. So in this case, we need to rotate this piece here before we bend it in order to get it to accurately produce this shape. Somebody just asked to make the grasshopper screen bigger. Yep, I can do that. But I'll put this definition online, so we can all have a look at it later. A few obvious fun things to do is using curves. These curves are the center lines of our pipes. So when we're bending them, sometimes the center line's useful, other times we might want to actually model pipes explicitly and synchronize those. So we use the Fologram mesh pipe component for making pipes. We can connect those up. We can specify a radius for our material. 8's probably a bit big. Maybe we're making things out of 8 mil pipe total. And what we're usually doing is we're coloring these holographic instructions differently depending on what the instructions are showing. So we would show a different color for the piece at the end of the bend compared to the piece at the start of the bend. Maybe the piece that's finished is going to be the same color as our remaining stock material, right? So before the bend, we could show that as being, let's say, a red outline. Be kind of cool. Or maybe we don't have an outline. And then after the bend, we have a green component. It's useful when you're fabricating things to make things slightly transparent. So you really want the holograms to be as faint as possible. So as faint as being able to, as faint as you can in order to still be able to see the hologram. And that's because you need to be looking at physical material and the holographic material at the same time. So now we have that set up nicely. So we've got our holographic material. We're also going to we're going to want to show which bend we're up to. So we're going to want to label this somehow. So we might want to show, okay, are we on, which bend are we on? Is it 1, 2, 3, 4, 5, etc.? And the other thing that we'll want to do is add an option to fabricate multiple parts. So rather than only fabricating this one selected curve, I want to make it so that we can select from multiple curves. And so what I might do is just draw a couple of other ones. So we've got this piece. And as always, we'll make them 3D. This one's fancy because it's a closed polyline. Okay, so we've got 3 parts there. And I think I won't worry about those for now for the demo. So two things remaining. One is we want to show the part that we're on and the bend that we're on, and the other thing we want to do is make it so that we can select parts. So showing the part and the bend that we're on, that's fairly straightforward. What we'll do is we'll make a user interface which is above our bender with some text. So I'm going to move, or really, I mean, the most flexible way to do this usually is to actually draw points in Rhino so that you can move them around and you have a lot of control over exactly where things are going. And so I'm going to do that instead. So we have a sync text tag component. I think Sean has shown you this one already. The text that we want to synchronize is, we'll use the concatenate component to synchronize our bend number. And I'm going to turn off the Y display for this thing because it's just going to be annoying otherwise. And we'll have a panel. Okay, so that's saying bend number 2, and the location of that text tag, rather than being at the origin, is going to be up here. The size is also pretty big. Let's make that a little bit smaller. Okay, so we've got some information showing us the bend that we're currently on. As we change our bend slider, that's going to change the bend that we're on. Next, let's add our part selector and show the part that we're on. So I've only inputted one curve here, but I'm going to add a list item component. And we'll synchronize these two, so we have bend and part as our two inputs. And then I'm going to set multiple curves. So we'll pick this part, and this part. Okay, so now we can go through and choose a part. Everything else in our definition works the same. So as we choose this third part here, we should be able to go through and pick a bend. Ah, that's not working yet. Why is that? Let's find out why. Because it's a closed curve, we've got to do something slightly different with our tool for selecting the arc. The arc isn't always the last thing in the list with this one. We'll fix that in a tick. Let's chuck that back on this part for now. So we can choose our part, and all we want to do is display that as some text as well. So I'm going to have another text tag down here showing the part that we're on. And let's show that on the point above. Okay, so we have part 1, bend number 3. So as we go through and change these sliders, we're going to see that update. So we get some really nice, clear visual feedback as to exactly what's going on there. All right, now debugging. So finding out why our closed parts work slightly differently. So as we split the list, we got 6. So with our closed part, the first line segment is actually an arc rather than a line, which is kind of interesting. And so with closed pieces, we actually don't want to reverse this list here, which is a bit of fun. So let's check if it's closed. So that gives us the arc. I mean, I'll just put this in the definition, so we'll be able to see it in a second. And then if it's closed, it looks like we also have to reverse that direction there. And I mean, this is also worth pointing out. It's why this definition here is a little bit simpler than the one that we end up using for actual fabrication, just because you always end up with some niche cases. So for instance, some benders bend in slightly different directions, so you end up having to flip vectors around to make sure that your bend plane is in the right spot. Depending on the material you're bending, sometimes you also need to flip a part from one side to another, which can make things more complex as well. So for now, I might just take this out because otherwise we're going to end up with a big messy definition. But if you're wanting to fabricate closed curves, it shouldn't be too hard to tweak the way that this vector math works, just so that you're ensuring that your bends actually are working. So just for the sake of the example, we're going to have another open component. Okay, 1, 2, 3, go. I mean, a really simple way to get around this, actually, come to think of it, is for closed components, and we did this on a project as well, which is why I remember it. What we ended up actually doing was splitting the component along midway through an edge, because we didn't actually want to start fabricating the component on an arc. For various reasons, it made it too difficult to fabricate. So we're gonna, if you just have closed components, like for instance with the Voronoi, as long as you split it along an arc. I think that might, it's ended up, that Rhino split didn't do it. But basically you have to be able to split a curve in the middle there. I mean, I can do it again. Or what we, just for the sake of a demo. There we go, and then that one will work. Just because when you fabricate something out of rod, like bent rod, you can't really ever make those match up absolutely perfectly. You want a little gap in it anyway. So for making these closed polyline parts, you'd want to parametrically go through and split the curve selectively in the middle of one edge, because it'll make it much easier to build. Alright, I'm going to internalize that data so that this all gets saved into one simple grasshopper definition, and I'll throw this online so that you can all have a play with it. So, and that concludes today's tutorial content. For tomorrow, the class will work slightly differently. So what we'd like you guys to do is, if you have a play around with the tool that Sean demonstrated today and extend it, muck around with it, make it do different things, maybe have a play around with this one. So you could do a layout of your different parts in Rhino, and then you have some diagrams showing how the bending works. You might also want to place a couple of images or sketches of your ideas into your Rhino model using the picture command, just like I was doing before. So let's say, you might even be putting in renders and things like that of your project if you wanted to, as pictures, and just publish that to AtStudio. So chuck it up into the Digital Futures room. If you're not sure how to do that, check out the live stream, the end of the live stream from yesterday, where I show you how that's possible. And then in tomorrow's session, the first half, Sean will be doing some more tutorial content, showing you how to create live sculpting applications. And then from about 3:30 Melbourne time, so 5:30 GMT AM, we'll jump onto Zoom and actually meet you face to face and have a chat about some of the projects that are in AtStudio. So that'll be a good way to ask questions, to give us some feedback on how you found the tutorials, to basically share ideas for what you might want to do with Fologram next, to have a chat about how AtStudio works. It's really a chance to discuss the work and to hear about your thoughts for what where this stuff might actually go. So make sure you've uploaded to AtStudio before the start of tomorrow's workshop. So before 4 AM GMT, make sure you've got some content in AtStudio. Check out the gallery in AtStudio if you want ideas for how to put work into it. There's some really great projects on there. Let me show you. So if you hit Explore Gallery, these are some examples of work that have been uploaded to AtStudio before in a kind of an exhibition scenario. So typically it's a combination of images and models. There's really no rules or right and wrong about what you can and can't publish here. Using things like color tends to look good. You can create saved views of your project, which makes it easier to present. It's really up to you, but AtStudio's there as a way to kind of share your work and your models. Don't be too precious about what you're sharing. It's just kind of more useful, I think, than screen sharing over Zoom, to have some 3D object for us to talk about. So yeah, it'd be great to see a bunch of stuff in there tomorrow, so that in the second half of the session we've got a lot to talk about. Just jump on the forum if you've got any questions or need any help with publishing anything. We're happy to help out. Okay, thanks for your time everyone, and we'll see you tomorrow.